everybody, it's Miss Manili. I'm going to go ahead through the review guide for sampling distributions, and I want to start with the flowchart that I gave you guys today. I just want to make sure that you understand that the very first decision you need to make has to do with the type of variable that's being measured. Is it quantitative or is it categorical? The way you differentiate, remember with quantitative data, it's all numbers. It's always going to be numbers, and you can take a mean. It would make sense to take an average of the numbers. So SAT scores, heights, any kind of measurement from something on an assembly line. Categorical data is it should relate very much to a binomial scenario where there may be several categories, but we're only interested in one being what we would consider to be a success. So it's either going to be listed in the problem as a proportion and you'll actually see a percentage symbol, or maybe it's talking about a survey that, where 700 people were selected for the sample and 350 agreed with a statement. That's another indication that we're dealing with a categorical situation or a proportion. So that, like I said, is the very first decision you need to make. The second decision you need to make is which distribution to use. And the best way to do that would be to test the conditions. So if I'm dealing with a categorical situation, if I'm dealing with yeses and nos or success and failure, the next thing I want to do is compute n times p and n times 1 minus p to see if I have at least 10 successes and 10 failures in my sample. If I do, then I'm dealing with a distribution for p hat. And I want to make sure that I define my random variable as p hat and as a proportion. So this column or this row is all of my random variables. So when you're asked to define your random variable, this is how you want to do it. So here I would say p hat represents a proportion of successes in my trials. If my sample was too small and I don't have 10 successes, so if this condition is not met, I'd be then looking at a binomial situation where, again, I'm going back to looking at the count of successes. And it's very important that you distinguish between the two, whether I'm looking at 5 successes out of 10 trials or 50% of my trials being successful, because there's a difference. If I'm dealing with a binomial distribution, I can only deal with whole numbers. So you don't want to write x as a percentage or a decimal. It must be a whole number. Whereas p hat has to be, in fact, here, let me write this down. So x can be 0, 1, 2, all the way to n. And with p hat will always be between 0 and 1. If we're dealing with quantitative data, we don't have those kinds of limits. X represents some measure, and it can be infinite. It's going to be a real number. It's going to be, it could be positive, it could be negative, it could be any number. So the conditions for using a normal distribution begin with the population. If the population is normally distributed, then it doesn't matter how big our sample size is. We can use a normal distribution to compute probabilities. If our population is not normal, then we need to look to see how big our sample is. And we have the central limit theorem that basically tells us that as long as my sample is very large, the sampling distribution will still be normal. So let's go ahead and take a look at some examples. The first problems on your review guide were just identifying the population in the sample and being able to recognize the difference between the sample statistic and the population parameter and use appropriate notation. So in number 1, it says the senior class at a large high school has 438 students. The principal collected data on 36 of them and found that their mean SAT score was 462. A subsequent computer analysis of all seniors showed the true mean to be 496. So remember, the population is who we're trying to find information about, like the entire group. Be as specific as you can. Don't just say students at the school. Be very clear. The population is going to be all 438 students, and actually you could even say in the senior class. And that actually would be more appropriate because we're told that it's just the senior class. So be as specific as you can. The sample then would be the 36 students that were selected by the principal. When we're dealing with the parameter of interest, or whether or not we're dealing with a mean or proportion, think about the numbers that are given to you. It says in the problem that we're talking about a mean math score. So that's a dead giveaway that we're dealing with mean. We're dealing with quantitative data. Mu is going to be the mean for the whole school, or at least for the seniors, for the population, and that's 496. It says all seniors have a true mean of 496. That's mu. That's our population. X bar is going to be the sample statistic. and that is going to be the mean of my sample, which is 462. That's going to be my sample statistic. In number 2, a Gallup poll asks a simple random sample of 1,785 adults whether they attended church or synagogue during the past week, and 803 responded yes. In fact, 40% of the adult population attended church or synagogue services. So in this case, I'm given a count and a total for my sample size. I'm also given a percentage here. This is a dead giveaway that I'm dealing with a proportion, or I'm dealing with a binomial situation in which I'm dealing with categorical data. So the population in this case, although it doesn't say that Gallup occurs in the United States, typically I believe that's where the Gallup poll occurs. So the population would be all US adults. And make sure you're specific. Don't just say adults. Which ones? In terms of the sample, it would be the 1,785 adults that were selected for the sample. In Part B, again, we've already indicated that this situation involves a proportion. And so which number represents the parameter, which number represents the statistic? Well, this last sentence, in fact, 40% of the adult population, it tells you right there that it's describing the population. That's going to be my sample, or I'm sorry, my population parameter, P. P hat refers to the sample statistic, and that I have to calculate as from my sample of 803 responding yes out of 1,785. And that again is my sample statistic. In number 3, we're looking at understanding the difference between bias and variability. Remember, bias deals with the center of the distribution. If there's high bias, then the center of my distribution is not going to be aligned with the population parameter. Variability deals with the spread, so you're going to be looking at how wide a distribution is. So in letter A, you can see the center of my sampling distribution is off-center, so that tells you that there's high bias. Relative to the other graphs, you can also see that the spread is larger, and so that indicates that there's higher variability. In letter B, you can see that my distribution is centered right over the population parameter, and relative to the other graphs, the variability is low. This is the perfect case situation. This is what we're aiming for. I shouldn't say it's perfect, but this would be like best case. If we take a look at letter C, this time again, we are off-center, so we have high bias, but we do have low variability. The problem is with bias, we don't even want to continue with our investigation because as soon as bias is introduced, it ruins the data. In letter D, in this case again, our distribution is centered over the parameter, so that's a good thing. And there's more variability than there was in letter B. This isn't a terrible thing, but it's not the best case. Obviously, we want to reduce variability as much as possible. So letter A would be the worst case scenario, and letter B would be the best case. Okay, so the next 2 problems deal with actual probabilities and computing probabilities given some information. So number 4, it says a news website claims that 30% of all Major League Baseball players use performance-enhancing drugs. So right away, I see a percentage symbol here. That tells me I'm dealing with a parameter, or I'm sorry, a proportion. And that is describing all Major League Baseball players, so that gives me a p-value of 0.3. In letter A, it says, indignant at this claim, league officials conduct a survey in which 200 randomly selected baseball players are tested. So this 200 corresponds to my N. Of those tested, 25% test positive. That 25%, since it's just referring to the sample, is going to be my p hat value. If we assume that the news website's claim is true, what is the probability that no more than 25% will test positive? So I've got to figure out, in order to answer this question, I got to know which probability distribution to use. So even though it asks you to define the random variable first, I think the very first thing we need to do is understand what kind of setting we have. What are the assumptions? What conditions are met? And we always want to look, if we're dealing with sampling distributions, we want to be able to see if a normal distribution is feasible. So the first thing I want to do is multiply n times p. And this is if we go back to our spreadsheet or our flow chart, since I know I'm dealing with categorical data, the very next thing I want to do is multiply n times p and n times 1 minus p. So n times p in this case is going to be 200 times 0.3. And that's going to be, I think, 60, which is greater than 10. And n times 1 minus p is going to be 200 times 0.7 and 140, which is also greater than 10. So since both of those conditions are met, I go back to my flow chart. Since both of those conditions are met, I'm working my way here. And so that means that my random variable is going to be p hat, and it represents the proportion of successes in n trials. Actually, okay. So I'm going to go ahead and write p hat represents the proportion of successes. I'm going to say the proportion of players who test positive for drugs. Okay, I'm going to go back to my flow chart to see what I do next. So once I've defined my variable, I also need to state my distribution. There's another condition that needs to be met, though, if I'm going to be using a normal distribution, and that tells me that my population must be greater than 10n because I'm sampling from this population without replacement. And so this condition is required anytime I'm using the standard deviation formula. So that's the other thing I want to state. The population of players has to be greater than or equal to 10n. Or 2,000. Okay, so I don't know how many baseball players there are, so this is an assumption I'm making. I'm assuming that the population of baseball players is at least 2,000. So those are the conditions I'm going to state. Now I want to describe the distribution. So this goes back down into the rest. I can conclude then that p hat is normal, and it's going to have a mean that is equivalent to the population proportion, and my standard deviation I can compute using that formula. So I'm simply going to say p hat is normal. The mean of p hat is my p-value. Remember, that's my population parameter, which is 0.3. And my standard deviation is going to be the square root of 0.3 times 0.7, because that's 1 minus 0.3, divided by n. And be careful, because I did see some people, when they were doing this computation, not keeping the 200 under the square root. So when I go to compute my standard deviation, I'm going to take the square root of 0.3 times 0.7 divided by 200. And I get 0.0324. Oops. Okay. Now I've stated my distribution. Now I want to determine the probability. So what is the probability that no more than 25% will test positive? Well, no more than would be less than or equal to. And again, I want to make sure that the variable that I use in my probability statement matches the probability or matches the variable that I defined. So these two things should be the same variable. And now I'm looking at my p hat value, the sample value that I got. If what we're saying about the population is true, if in fact 30% of all baseball players use performance-enhancing drugs, then what are the chances of me getting a sample of 200 with a sample proportion where less than a quarter of those athletes use the performance-enhancing drugs, or at least test positive for that? So this is the setup. Anytime you're using a normal distribution, you must compute the z-score. And so we do the z-score by taking our sample statistic and subtracting the mean and dividing by the standard deviation. So I'm going to hit second enter here so I don't have a rounding error. And I get negative 1.543. And the next we want to compute the probability. So you can compute the probability in terms of p hat, or you can compute the probability in terms of z. Since I just computed z, I'm going to do it that way. So I'm going to go to my normal CDF. And remember, you always need to enter the lower bound and then the upper bound. So since I'm looking at the probability that z is less than something, my lower bound is really going to be negative 9999999. My upper bound is going to be, I'm going to use second answer since I just figured that answer out. And then this will avoid rounding errors. Since I'm dealing with z, I'll use 0 and 1 as my mean and standard deviation. And I get 0.0614. You could also compute this probability using p hat, so I'll do it that way as well. My lower bound will continue to be negative 99999, but my upper bound would be 0.25. Since I'm using p hat, I'd also want to make sure that I enter the mean of p hat, which is 0.3, and the standard deviation, which I computed to be 0.0324. Now, since I'm entering in all the other ones, I didn't enter in a rounded number, I entered in the actual value. In this case, I'm entering in the rounded standard deviation, so when I compute the probability, it might be just a teeny tiny bit different. Very, very similar though, 0.0614 if you round it, which is exactly what I got before. And so then sometimes there are going to be questions that follow. So for example, if I asked, you know, based on this sample, would you suspect that the claim about the population is untrue? So like, let's say we've got these league officials that now are challenging this 30%, and they take a sample and they find that it's only 25%, does this give them evidence to prove that the claim is false? Well, notice that the probability is 6%, and we draw the line at 5%. So if the probability of getting the sample was really, really small, like if it was 2% or 1%, then I shouldn't have seen that result. And that would give these league officials some evidence against the claim that this website made. But in this case, even if that claim is true, if 30% of all major Major League Baseball players actually use performance-enhancing drugs, if that's true, there's a 6% chance that I'll get a sample of 200 that include 25% of them using the performance-enhancing drugs. So this would not give me evidence against the claim. If it was a smaller probability, then it would. All right, let's take a look at letter B. Same scenario, we're still looking at the same claim of 30%, but this time instead of looking at 200 athletes, we're looking at 20 randomly selected players. And we want to know the probability that no more than 5 or 25% will test positive. So this time, if I think about my conditions, because remember that's really where you should start, if I think about my conditions, n times p, well, my p is still the same. My p is still 0.3, but this time I'm only looking at 20 athletes. Whoops, so that should be a 20, not a 30. So that means I'm looking at 20 times 0.3, and that's only 6. And since that's less than 10, I can't use a normal distribution. I can, however, if we go back to our spreadsheet, if the condition isn't met, I can, however, still use a binomial distribution. So where now x, my random variable, instead of representing the proportion of successes, and I need to be very clear that I differentiate here, x would represent the number of successes in n trials. So I'm going to go ahead and say x represents the number of players who test positive in the sample. And then I would say that x is distributed binomially with n and p. But notice that I do have a condition here. I have to assume that these players are independent of each other. So I'm going to go ahead and state the rest of my distribution. So n in this case we said was 20, and p is still 0.3. And the other assumption I have to make, though, is that we have to assume independence between the players. Okay, now I have my distribution. Now I want to determine the probability. Be very careful now. If you're using a binomial distribution, you must only refer to whole numbers. You cannot put in that 25%. So we're now looking at the probability, and again, make sure your variable is consistent, that x is less than or equal to 5. Since I'm dealing with a binomial random variable, there's no need to standardize. We only do that with normal distributions. So at this point, I would go ahead and choose my binomial CDF. And since the inequality is already less than or equal to, I don't have to change it around at all. I can simply write in. Now, just be careful. With a binomial distribution, you enter the parameters in first. So if you have an older calculator, you would type in the 20, a comma, a 0.3, comma, and then the 5. And you get 0.4164. Okay. So it definitely would not be unusual to have less than 6 players in this case, I guess, in a sample of 20 test positive, even if in fact the true parameters, 30% of these players use performance enhancing drugs. The other thing, just in case, just to remind you, if I was asking for the probability that X was greater than or equal to 5, I can't input that directly into my calculator as is. I have to take the complement. And the complement of greater than or equal to 5 would be 1 minus the probability that X is less than 5. But even if I write it like that, I still need to adjust it a little bit more. Because in order to use the CDF function, I have to have it written as a less than or equal to. And so the only number that is less than or equal would correspond to the number 4. And so then I would do 1 minus the binomial CDF, NP, and then 4. Okay. In number 5, now we're completely switching the scenario. It says, assume the duration of human pregnancies can be described by a normal model with a mean of 266 days and a standard deviation of 16 days. So what I've just described to you is the population. The fact that I am describing a population to you is indicative that I'm dealing with quantitative data. The other thing you can tell right away is it's giving you a mean and a standard deviation. So if we go back to our flow chart, it's quantitative. When you're dealing with a quantitative situation, you're going to be given the sample size, the mean, and the standard deviation. And the very next question you want to answer is the population normally distributed? In this case, it is. And since it is, I can go ahead down this set of branches. Okay, so, and I always want to kind of start with my assumptions. So I would go ahead and say the population is normal. It's given. It's not really an assumption, but I don't have to assume that. It's stated in the problem. So if the population is normal, I want to think then, am I dealing with a sample of one or a sample of many? And in this case, it's not as obvious as the other one. So in part A, it says, what percentage of pregnancies should last between 270 and 280 days? It's essentially, if I were to choose someone at random who is pregnant, what are the chances that her pregnancy would last between 270 and 280? So this is actually looking at an individual pregnancy. And so I would define X, and it tells you on the flow chart. X represents the measure from one individual. So I would say X equals the duration of a pregnancy, of a human pregnancy. And then I'd talk about how X is distributed. And remember, we're talking about the population. All of this information is given to us. X is distributed normally with a given mean and standard deviation. The mean we said is 266 days. The standard deviation is 16. Again, this is given. Now I want to determine the probability that a pregnancy would last between 270 and 280 days. Again, I'm using the random variable X, not X bar. And I need to standardize both values. So this again is using my X value minus the mean divided by the standard deviation. And if you do this, you should end up with a z-score between 0.25 and 0.875. And when you go to do your normal CDF, it doesn't matter if you're dealing in terms of X or Z. I'll go ahead and do X again. So I'd be looking at my lower bound is 270, my upper bound is 280, my mean, I'm told, is 266, and the standard deviation is 16. That tells me about 21.05% of pregnancies last between 270 and 280 days. And that's basically how I'd answer the question. So about 21% of all pregnancies will last between 270 and 280 days. Part B is asking something a little bit different. It says, suppose a certain obstetrician is currently providing prenatal care to 60 pregnant women. Okay, so prenatal care to 60 pregnant women. Now I'm dealing with a sample of 60. What's the probability that the mean duration, so now I'm talking about the mean of a sample, that the mean duration of these pregnancies will be less than 260 days? Well, remember we said the population was normal? Since the population is normal, I can say that X bar is also normal in this case. But we also know that since n is equal to 60, which is greater than 30, both of those conditions are met. And so since I'm dealing with X bar, I want to make sure I define it. So I want to make sure that I say the mean duration of pregnancies in samples of 60 women. Okay. And when I'm stating the parameters for my distribution, the mean is still going to be the 266. But this time my standard deviation will be 16 divided by the square root of 60. And that becomes 2.0656. And if I'm using this formula, I also have to remind myself that the population must be at least 10 times the sample size. So I'm looking at 600 pregnant women. And because I don't know, I'm assuming that the number of pregnant women is more than, 600. Okay. In the last one, we're finding the probability. And so this time, I'm trying to find the probability that the mean duration is less than 260 days. So make sure that you're dealing with X bar in this case. Oops. And I'm looking for the probability that X bar is less than 260. I still need to standardize it. And so that gives me a z-score of a negative 2.905. And when I find the probability here, I get 0.0018. And notice how much smaller, well, actually, they're asking two different questions. Never mind. I was going to say the probability is so much smaller, but we're asking a different question here. And so in this case, I'm talking about what are the chances of having a sample of 60 women that have a mean pregnancy length that's less than 260 days. Well, think about it. If the mean is 266 days and we're looking for a sample value that's almost a week early, what are the chances of having a sample of 60 women that deliver on average a week early? I can expect that probability to be pretty small. The last question, and this is an important one to note, says the duration of human pregnancies may actually be skewed to the left since doctors induce labor when women surpass their due dates. So if we think about, initially we were saying pregnancies should be normal with a mean of 260 days, 66 days. So, it is possible that women could, give birth at day 200. I mean, lots of women give birth early, but I'm probably not going to see a lot of women giving birth after 320 days because doctors are going to induce. There's only so far a doctor is going to allow a woman to stay pregnant beyond her due date. So the actual distribution is probably much more skewed to the left. So the question then becomes, how does that change your answer, if any? Does it change your answer to parts A and B? Well, in part A, because I was relying on the population being normal, that's the only way I could compute this probability. I wouldn't have been able to compute the probability if it wasn't normal. I would have needed to know what the distribution was. However, in part B, because my sample was so large, because it was greater than 30, my sampling distribution would have been normal regardless of the shape of the distribution. So my answer to part B would not change. And I do want to just remind you that there are some remediation problems attached to Blackboard if you need a little bit of extra practice, also on the back of your study guide. But it is expected that you guys have the conditions memorized. The formulas are on the formula sheet for you, so you don't have to have them memorized, but you do need to know when to use them. So let's just review. The very first decision that you need to make is whether you're dealing with quantitative or categorical data. Quantitative is when we're dealing with mean or x bar. Categorical is when we're dealing with p's and p hats. Now, if your distributions are really small, then we might be dealing with an x being the number of successes, or in the case of a quantitative, x being the measure of one individual. But for the most part, this whole unit focuses on sampling distributions for p hat and x bar. So make sure you understand this flow chart. If you need some extra practice, like I said, there's remediation problems posted to Blackboard. You could also do the chapter review problems in the back of the chapter. I'm not going to be here on Friday, but I will be available Monday morning for Bulldog Block if anybody needs some extra help.